Hi, everyone. My name is Bhagat. I'm from Google, and this is Reshma.
Reshma Sudarshan from Intel.
And hi, Brian O'Connor from ONF.
So we are here to talk about pins. It was just introduced in the last talk as well as one of the major items coming in this Sonic release. So without much further ado, let's start. So as you all know, Google has been a major user and promoter of SDN in the data center. We love SDN because it helps us do simple traffic engineering as well as easier debugging. SDN the controller has the entire network state available to it. It's pretty useful in debugging. And it also allows control plane and data plane separation. We're able to take the control plane, run it in dedicated, modern processors, very fast, compute optimal routes, and then send these routes to the entire matrix of switches we have, thereby programming every switch precisely as we want to. Over the last few years, we have seen that SDN and remote controller adoption has been growing, not only just inside Google, but also outside. And along with Intel and ONF, we have been working on getting SDN mainstream. In this talk, we are going to describe the efforts that we are taking to do that, as well as how we are bringing SDN mainstream to the community.
Sonic is a mainstream network operating system with over 4 million switch ports deploying Sonic as of right now, as per the Loro study. Being generic and flexible, Sonic is being extended to other network devices such as SmartNICs. As the packet transformation happens within each device in the network from edge to cloud, Sonic is capable of managing both the hardware and software components. At Intel, we are building an underlying framework, a hardware programming layer, that is designed to make these network devices interoperable by being compatible with Sonic. Its modular and container-based architecture helps it be a scalable and secure NOS that our customers are extending the Sonic to write their own custom applications and have this common way to manage all their applications. The other networking paradigm that's taking the industry by storm is SDN. SDN in Sonic allows opt-in path for controller-managed switches, which integrate seamlessly into the data center infrastructure with visualization and analytics.
So P4 is a language that's been taking the industry by storm. We're seeing P4 programmable ASIC targets, we're seeing P4 programmable FPGAs, and we're seeing targets that are available on the CPU in the form of DPDK and eBPF. For this reason, we see P4 as the future definition language for programming or expressing the data plane functionality. Now, if you know anything about Sonic today, it's not based on P4, it's based on Psi. And Psi is a collection of diagrams, like the one you see on the left, header files, and English language descriptions. The first thing that we've done as part of this transformation is to take those specifications and convert them into the P4 language as a machine-readable, unambiguous specification of Psi. This is shown on the right here, and this is just a snippet of the fixed parts of Psi that we've modeled in P4. Now, once you have things in P4, we can do a bunch of things automatically with the compiler. The first thing we can do is we can lay out the hardware in the case of FPGAs, programmable ASICs, or CPU. But P4 also expresses the control plane contract between Sonic and the SDN controller in unambiguous terms and entities that are described precisely by the P4 program. Lastly, even if you don't have a programmable target, P4 is still useful for testing and verification. We can use static analysis and fuzzers to generate system tests and test plans. We can also take our P4 program and run it in behavioral models and simulators and run real network traces through the pipeline and compare them to our hardware to find new classes of bugs. Putting this together, PINs is a solution, or the P4 integrated network stack is a solution that enables SDN on Sonic. We started by modeling the pipeline using P4, both for fixed and programmable targets. We then add P4Runtime, which is a standard open silicon independent gRPC service to enable remote controllers to talk to the Sonic devices. And then the other part of SDN that's enabled is through the management, telemetry, and operations. And for that, we rely on the protocols and models from OpenConfig. So when you take the SDN control plane, P4Runtime, GNMI, GNOI, and the OpenConfig models, put them together on top of Sonic, we have an SDN solution that enables the next generation of SDN. On the right side, we're not focusing on it in this talk, so this will probably be the last time we mention it, but we already have the UMF project within Sonic, which is working on upgrading GNMI and GNOI, and we're relying on that and enhancing that as part of this program.
Let's move on to the architecture. So as we worked on integrating Sonic and SDN, which are two large ecosystems that have developed independently for multiple years, we faced multiple challenges. To give you a picture of some of the challenges we faced, I would like to illustrate one particular aspect that's different between Sonic applications and SDN. So today, Sonic applications compute their intent and write it to the application DB. The moment they write it to the application DB, their job is done. Once it's written, it's up to Swiss and its multiple Orchagents to realize that intent. Swiss takes it up, writes those intent to the ASIC DB, and retries if necessary. SDN, however, is a little different. SDN controllers generally have a matrix of switches available to them. If a particular switch is not able to realize an intent, the controller can use other switches in its matrix to realize some of these intents. So it's very vital for the controller to know if an intent is realized or not. It's important to know the response. So this introduces the response path to the Sonic. We are introducing in this architecture P4RT, a new ARC in Swiss that will publish responses. It tries once for any intent that is published in the application DB, finds out the response, and lets the application know, lets the remote controller know the failure or success of the programming so that the controller can then take remedial action. Moving on to the architecture now. So left side of the picture is probably very familiar to you. It's Sonic, applications at the top, Swiss and Orchagents in the middle, and SyncD at the bottom. On the right, let's start from the top. We have SDN controller running its multiple workflows, computing what needs to be programmed in each and every switch, and sending that information through gRPC to P4Runtime. P4Runtime is a new app. It is capable of receiving these gRPC messages, translating them to a format that's human readable, and writes them to P4Runtime tables in the application DB. The P4R carries on from there, picks it up, writes it synchronously to ASIC DB, gets the SyncD response, and populates that response back into response tables. Response tables is a new addition that we are doing in Sonic. It provides an accurate picture of the current state of the system. What is exactly programmed in the ASIC? The applications get to know. Not only the applications get to know, but they get to know in the format that they understand. So the response tables are in the exact same schema as the app DB tables. An application can compare and contrast and know what failed, what passed. It can even have partial failures. So we think this is a revolutionary new way to give back a response. And we believe that local applications in Sonic will start adopting this as well. And as we move ahead to the next slide, let's zoom in into the P4Runtime app and look at what it provides. The P4Runtime app runs a P4Runtime server capable of connecting to multiple clients and arbitrating between them. This allows high availability of P4Runtime clients. A client fails, another client can take over. So you can run remote controllers in a high HA fashion. It also allows the remote controller to send a pipeline. But then this is Sonic. The pipeline is Psi. It's a fixed pipeline. There are a few elements, though, in the Psi pipeline that are modifiable. For example, ACL tables have multiple match parameters, and you can devise your own ACL tables with different key parameters. Also the sizes. And send this down to P4Runtime app. P4Runtime app will program this into the pipeline. In addition to these, P4Runtime supports the write API so that the controller can send requests that can be programmed in the ASIC. It also supports the readback API. So the controller can run audits. It can read back what is present and verify whether everything has been achieved at any time.
In keeping with the Sonic methodology, to realize SDN via a creation of application and agent layers, and to implement the network configurations from the SDN controller through the P4RT APIs. P4 Orchagent is a new module that Pins introduces into Sonic, and it lies in the Orchagent process in the SWSS container. The P4RT server, while it receives the messages, the P4 requests from the SDN controller, and translates them into the P4RT entries in the application DB, P4 Orchagent manages this table in the application DB by itself and with those entries with the P4RT prefix. It translates these entries into the ASIC DB, after which the serialization, deserialization happens in the syncd to make the corresponding Psi API calls to program the switch hardware. The P4 Orchagent interacts with other Orchagents, such as ports org and VRF org, to resolve the interdependencies, and also the reference counting of the remote managed Psi objects. The P4RT interface requires the response for every programming request to match with the exact state of the hardware. For this reason, the Orchagent and syncd are placed in the synchronous mode so that the P4 Orchagent gets the exact state of the Psi API calls. The Orchagent implements a notification channel to relay this information all the way up to the Sonic P4RT application. The P4 information passed from the SDN controller in the form of gRPC write is intercepted by the P4RT container that's newly been added. In this example, we are installing a route to a next hop. The match keys are the VRF ID and the IPv4 destination address, and the action parameters are next hop S1. While these P4 information is sent from the SDN controller, is being translated to the application DB representation, our P4 Orchagent converts and translates the next hop S1 to its own object ID and the VRF ID to its own object ID, and this it does by talking to the VRF Orchagent in the process. So it relies on these other Orchagents, and resolving interdependencies, it adds these entries into the ASIC DB. The response status is recorded and marked in the application state DB. So Orchagent has the actual state of the SCI API calls in the ASIC DB, which it propagates up to the application state DB, which in turn propagates to the P4RT client as part of the response status.
Let's talk a little bit about packet I/O. So Sonic today supports packet I/O through Linux network devices or NetDevs that are present in the system and brought up when interfaces come up in Sonic. So these are the Ethernet 0, 4, 8, et cetera interfaces that you'll see today. And when an application sends packets to this NetDev, it's transmitted out the associated front panel port. When packets are received and punted via ACL rules, they're received via these interfaces. In pins and P4Runtime, these NetDevs work super well for sending packet outs from the SDN controller. We send packets using P4Runtime to the P4Runtime server, which then forwards the packets to the associated NetDev for the packet out. However, sometimes the P4Runtime server or the SDN controller doesn't want to specify which port a packet should go out on. For example, if you're doing testing and you want to test the state of the switching ASIC, if you want to broadcast packets and don't want to send multiple copies from the SDN controller, we need a way to specify that a packet should be processed by the switching ASIC, not directly transmitted out an egress port. To accomplish this in Sonic, we've added a new NetDev called submit to ingress. And when packets are sent to this NetDev, they come from the CPU port from the perspective of the ASIC, and they're processed by the standard ingress pipeline. Switching to packet receives, we could have received packets through the NetDevs like standard apps, but the SDN controller needs a little bit more metadata than just the ingress port, which you can derive from the interface name. We need things like the target egress port. What port would the packet have gone to had we not trapped it? We also want the ability to capture an application context in the form of a context cookie that we can tell at the SDN controller which application or which rule requested these packets. There are other forms of metadata that applications will need in the future, but those two are two examples. We solve this problem similar to the way SFlow captures packets in Sonic today. We have a special driver that filters packets on the way in. We can read the additional metadata off the frames in the kernel, and then we put them into a GE Netlink message, which is sent over a dedicated socket to the P4Runtime application. From there, we wrap it in P4Runtime protocol and send it to the SDN controller. So in this way, we've augmented the packet I/O capabilities in Sonic, and we think this mechanism is something local apps will be able to take advantage of as well.
Time to talk about demos and use cases. So let's talk about a well-understood, well-known use feature, WCMP, and its importance to the data center. In a data center, the goal is always to maximize utilization. You want to maximize the network that you have. And plain old eCMP or even static WCMP is not enough to make this happen. Let me explain. Workloads that run in the data center are often not known a priori to the network designer. They also keep changing with time. A data center keeps getting built out. It includes multiple generations of hardware. So weighted cost is an important, crucial element. And last but not the least, unfortunately, we still have failures happen every now and then. It adds dynamic nature to routing. There are links that fail, switches that fail, alas, there's even power that fails every now and then. And in all these cases, the controller has to act very quickly and restore optimal routing. The controller is in a unique position to do this because it knows the entire network state, it knows the topology, and is able to do that. There are references here to a much more detailed stage-by-stage explanation in the link that is shown at the bottom. And as we move on, we have a demo on the floor today. It has multiple ASICs from different vendors showcasing pins stack. The pin stack is running on Arista and Acton switches, has Broadcom and Tofino ASICs, and it's today controlled by the SDN controller SD Fabric running on ONOS. ONOS connects to these switches through P4Runtime and GNMI, manages the topology, and programs them using WCMP. Please stop by the ONF booth, which is very near the Experience Center, and take a look.
Discussing the roadmap. For the first pins release, these are the set of MVP features that we have added and are being upstreamed to the Sonic 2021-11 release. This includes a mechanism to completely configure the layer 3 path along with the weighted cost multipath that Bhagat described. In the pins sci.p4 program, it describes the pipeline to achieve layer 3 routing, full IPv4, IPv6 routing, ACL, and WCMP, and the pipeline changes for this from the user level. And following the Sonic release cadence going forward, we intend to add to the sci.p4 program with additional features including 802.1q, VLAN support, SVI, as well as in the future releases, VXLAN and other tunnels as well. The most important system level enhancement that we have done part of pins that we have heard today is the response path in the P4org. This, we have received very good feedback from the community, and we plan to extend this feature of the response path in other Sonic Orchagents going forward. We also have added a feature to dynamically add match action tables and to realize the user level enhancement through those tables in the existing Sci pipeline, and this will be coming soon. And last but not least, the robust test framework to test all of this enhancement has been added with the focus not just on P4, but also encompassing the GNMI. And this test framework is something we will be upstreaming in the next Sonic release.
So let's take a quick view at the community that's been building this. In 2019, Google, ONF, and Intel came together to form a working group to work on the design for how we'd bring SDN and P4 to Sonic. In the 2 years since, we've added a number of companies, Arista, Broadcom, Cisco, Innovium, and NVIDIA to the group. And they've all brought new use cases, they've brought new hardware, and they've worked on us to help validate the designs and enhance them. Bhagat mentioned one kind of critical use case from the Google perspective, which is WCMP. And through working group, we've also looked at additional data center use cases. We've looked at the 5G edge cloud. We've looked at hybrid control plane use cases. And we want to continue to grow this these set of use cases with the community. We're super excited as a community to bring you a first version, our MVP, in the November release, which should be available later this month. And we're excited to continue to build this out with all of you going forward. So here's our call to action. We've talked to you a little bit about what we've built. We've talked to you a little bit about where we think this is headed. But for all of you, I think the first next step is to try it out. Download the latest Sonic release, turn on the P4Runtime container, and give it a try. See how it works for you in your use case. Once you've tried it, if you have feedback or you have suggestions, enhancements, the Sonic Pins subgroup is the forum where we expect a lot of this contribution and discussion to take place. If you want to get a little bit more under the hood, we have a series of high-level designs, which are part of the Sonic repository. We cover all of the things that we've talked about so far in quite low-level engineering depth in those designs. And when you're ready to help us build some new things, the MVP pull requests are all up. And I'd like to draw your attention to the Sonic Swiss repo for P4Orc and the newly minted Sonic Pins repo for the P4Runtime container. So where this goes is kind of up to all of you. We have a small community. We're looking to build this out. But it's what you do with it and how you choose to adopt it that are going to, is what's going to push this forward and what's going to help drive SDN towards more mainstream. So the three of us look forward to welcoming you all to the community, supporting your platforms, building your use cases, and helping you transform your networks. Thanks for your attention.
Thank you.
We had one question online asking how do you compare this to the Stratum project? There's a Stratum project with P4 layer over Psi, same idea, but without the extra layer of Sonic DB and SyncD. What extra benefits do you have compared to Stratum?
Sure, I can take this. So at ONF, I actually lead both the Pins work and Stratum projects. For those of you that don't know, Stratum's a project that was originally worked between Google and ONF on bringing just a thin P4Runtime service on top of a Switch SDK. What I would say from a comparison perspective is with Stratum, there's no base pipeline, and there's no local control plane. So if you're running pure play SDN, Stratum works great. But you have to do everything yourself. You define your pipeline, and you bring your own control plane. Where Sonic differs a little bit is we have a baseline pipeline that everybody starts with, which is our Psi.P4 pipeline. We also have an embedded control plane, which is FRR, TeamD, for lag support, LODP, et cetera. And so with Pins, you can take an image that's running Sonic today, fully disaggregated distributed networking protocols, and you can slowly turn on features or opt into SDN on a use case by use case basis where there's the greatest amount of business value. So if you're running traditional networks or you have Sonic deployed and you want to start to get some SDN benefits, Pins is a really good place to start.
Great.
That's a great answer. And to add to it, one of the first things we did when we started on this path was to enable the SDN controller and turn off the local routing in the Sonic box and just write down to the AppDB the routes that we want to get programmed. And that just worked awesome, right? So you can basically just bring Sonic in, turn on this programmability, and start working immediately.
Nice, thanks. Got a couple of questions, looks like?
Yes, I noticed that the list of companies on your previous slide included 3 switch ASIC vendors. Is Google already deploying switches with multiple vendors providing switching ASICs, or is that a plan for the future?
So as I mentioned, this is something that we are looking at to help SDN go mainstream. Google is primarily focused on SDN and is definitely interested in enabling SDN be used, adopted widely, and we are committed behind SDN.
Thank you.
To give a little bit more flavor on some of the other vendors, we mentioned that we have both Broadcom and Intel Tofino running in our demo today. We're also working with Innovium on Terralinks. We're working with NVIDIA on Spectrum, working with Cisco on Silicon One. And there are customers and use cases that we see for each of these vendors with SDN and Pins going forward.
Thank you.
Yeah, so the question about Stratum is a bit interesting because you said you have the local control plane. How you can avoid split brain situation? Because you have already the control plane, you have the decision center, you're moving it out, you must be in sync. Because it can be possible that your control plane, local one, is conflicting with your SDN controller. And then you're in a situation that it even breaks everything or even makes things much worse than it should be.
Do you want to take this on?
So,
Go ahead.
Just a quick line here, and maybe I'll hand it off to Brian and Bhagat, is that the split brain scenario is a very important question, and that we have addressed it by design is something I'd like to say. with a bit of network design and more planning and things like separation with VRF in L3 is something that we can avoid that. And we have role-based control of controller as well. So that's something we will be enhancing even more in the future. Bhagat and Brian, you want to add to it?
Yeah, so to add to that, so one of the things we wanted to enable here, as Brian mentioned, is opt-in. Right? That's a key factor. The difficulty, again, referring back to Stratum, was that you need to bring everything. And here we have something where you can decide which applications to be local, which to be remote. Right? That enables you right away to start working on this. And if you are running the same application remote and local, then the overall architecture needs to cater to and figure out how to establish a zero conflict scenario. In the case of routing, you could decide some VRFs being managed locally and some VRFs being managed remotely. So for each and every application, there may be different techniques that we need to adopt. At this time, we are looking at running different sets of applications at different places. And as we go ahead, we look forward to bringing more things into here.
All right. Just one last quick question. Yeah, because we're here at the end of the time. The streaming is all done.
All right. Jay Kumar, Broadcom. First of all, thank you for the wonderful presentation. That was awesome. I have a quick question. So on the stack, on the pin stack, we mostly talk about P4 runtime, P4 entities, probably some support from the P416 compiler constructs. How do you see this going on in a different vendors which natively do not support P4? So that's the question.
Sure, I can take this one. So one thing I want to show in our architecture slide is that, sorry, this one, is that today we don't require that vendors support P4 whatsoever. And for the fixed and configurable parts of the pipeline, like routing, L2, ACLs, et cetera, there's no vendor P4 support required at all. We don't actually add anything at the syncd level, and we don't add anything new to the ASIC DB. So the entities that we're writing from P4Orc go into ASIC DB, and they're handled by regular SI 1.81, as you can use today. Where we require some degree of vendor support is when we start talking about extensibility. So if users want to add custom tables, new header formats, new protocols, that can be described in P4 as well, but it requires a little bit of vendor support. And vendors can choose whether they want to have a compiler that automatically maps this to hardware, or they can have a semi-automated or a manual mapping to map these new P4 runtime tables to their low-level SDK. And we see from different vendors in different phases of P4 readiness or adoption, a whole spectrum of approaches. So it could be the case that someone defines a new table in P4, and as a vendor, you say, I have an SDK call. Let me just map this down directly. The same way you would do for a SI extension if someone gave you a new header file today. But if you have a programmable target that understands P4, then you can automatically augment your pipeline, and you can give a little bit more into the customer to help themselves, basically.
Thank you, Brian.
Yeah.
Thanks a lot for everyone's questions, and hopefully if you all are available afterwards, and I know we had to cut off a little bit, but we've got some more questions if you're around. Let's help thank the speakers. Thank you all.
Thank you.